All right, greetings, class, and welcome back. We're going to start on chapter 2 today. Last time we talked about methodology, and now we're going to talk about different types of data and then also how to organize that data and pull out some like real basic, like classifying and descriptive information from that data. And we'll also talk about different ways to display data just a little bit. We're going to touch on that. And so this would be a pretty simple one. So we're going to look at some graphs and tables and talk about different types of data. So here we go. Let me share my screen with you. All right. So when talking about data and distributions, one reason that this is a good starting point is because if you have a lot of data, you can feel kind of bogged down or overwhelmed by just the sheer amount of it. And you need some way to create a system for managing that data so that you can see it all in one place and you can make it easier on yourself for understanding it. Because in its raw form, it could be overwhelming, right? So you want to feel like this guy in this cartoon, like this tidal wave of numbers is just coming for him and out to get him, right? We want to find ways to organize that data so that'll be easier for us to manage. But before we do that, let's talk about some different types of data, because of course not all data is the same and you shouldn't treat all data the same. So this slide says measurement scales. Like there's four types of measurement scales. So that means there's four different ways. There's more than that, but there are these four different ways to measure and record your observations. And of course, that creates a different type of data. So you just want to make sure those match. Like if you're using this first type of data, which is nominal, then there's certain types of analyses you do for nominal data, right? And then the next type of data we'll look at is ordinal data, and there's a different type of analyses, different set of analyses that you use for computing and understanding ordinal data and so on. So there's these four types of data we're going to go over for our class, and we will look at them. Even though there's four types, we're really going to look at them in like three different categories as we go on with our class. So let's start off with the type of data that comes from a measurement scale that really gives us the least amount of mathematical information. Now, I don't mean that like it's not valuable. It's just you can't do very much math with it, but it might be crucial information, for you to have for your study. Right. So the first is nominal data, or sometimes called categorical data. But categorical data can be two different types of data. So we'll say this is nominal data, but it's discrete, right? So it's like you're in one category or another. So it can be dichotomous if you only have two options. So a nominal scale, though, it doesn't tell you any kind of amount of anything. It's just used as a classification. So the number can be important for you because you want to know what group, say, people fall in, and if it's something like, say, like ethnicity, and maybe you have participants and they're from seven different, you know, ethnic backgrounds, then you might want to keep track of that in your data. And so you assign each ethnicity a number, but you can't really do any math with that number. You just know, oh, you're in group number one. Okay, you are Hispanic, right? Oh, you're in group number two. Okay, you're Asian, right? And so on. So the numbers are there just to help you categorize people or put them into a certain group, but they don't have any like mathematical weight, right? So you could think of lots of different examples. Most demographic examples you'd see on surveys, like I mentioned, ethnicity or sex or gender, right? And then marital status, your hair color, your housing style, all of that is nominal. Like it's all numbers that we use, but you can't. It's limited, right? You guys carry these around in your pocket all the time, right? You've got things like your driver's license number as an example. Those would be your ID number at BC. Like all that is just ways to identify you and classify your data. All right, so there's not a whole lot we can do with nominal data, but there are some interesting things we can do, and we'll get to that in chapters as we move on through the class. Okay, now the second type of data, now we're getting a little more information. It's a little more than just a simple discrete classifier, but it's still limited, right? So we're going to look at an ordinal scale of measurement next. And if you think ordinal, think order, rank order. If you could put things in rank order, then that's a step above nominal data, and you can do a little bit more with ordinal data than you can with nominal data. but they don't always make sense mathematically still, right? There's some subjectivity there, or there's some missing information there about like the increments between numbers. So like a movie system rating is perfect. If you're like me, right now, since we've all been at home during the pandemic, then we're watching like a lot of movies streamed to my TV. So sometimes you might choose what you want to watch based on like how many ratings it gets. And then we kind of do that in our house. Like my wife and I, we really like horror movies. Watch horror movies sometimes at night. And if you are horror movie fans, then you know that like most horror movies are, in my opinion, just terrible, right? And there are some good ones out there, but they don't get a lot of advertisement, so it's hard to figure out like, okay, which one's good, which one's bad. And so we'll look through, say, like Netflix, for example, and we'll go to that that genre of movies, and we'll look at the horror movies and we go, okay, there's these like six that kind of look interesting, but we've never seen any of them. Which of those six are we going to watch tonight, because we want to watch something good, right? And so we look at it and we go, oh man, I've never seen like The Exorcist, which probably gets like 5 stars. People like The Exorcist a lot, right? You go, oh, all right, there it is. And then maybe some other movie like I don't know, what's one that came out that we saw recently. What was that one? Drag Me to Hell. That was one we watched recently. And that one got like 3 stars. So you can see from this like collective ranking from people that Drag Me to Hell got 3 stars, Exorcist got 5. So is Drag Me to Hell 3/5 as good as The Exorcist? It's like, oh, that doesn't make any sense mathematically, right? And you say, well, we know that people like The Exorcist more. They think it's better. Well, how much more? How much better? You go, well, like 2 stars better, dude. 2 stars worth. It's like, I don't know what that means. So it doesn't have really mathematical value. It's hard to like divide and multiply, with stars. But it gives you an idea of how to rank information. Or another example might be this. If we don't want to take the movie score example, let's say that as a class, I said, hey, meet me at the park by my house and we're going to have a race. And we're going to race from one end of the park to the next. And I'm going to time you all. Right. And maybe to give you an incentive of like, I'll give extra credit to like the first 5 runners that come back to me across the finish line. So you're going to try really hard. Right. You notice how I left myself out of the race in my example. Yeah. But anyway, so you run to the edge of the park and then you come back, right? And let's say that you came in third, right? You personally, you came in third and you ask me, well, how much time was I behind the second place? I'm like, I don't know, you were slower. Well, how much slower? I don't know. I didn't use my stopwatch, so I can't tell you. I can tell you you were slower than second place, but you were faster than fourth place. You go, oh, how much faster was I than fourth place? I can't tell you that, right? I didn't measure it in units of time of any kind. I just know that, where you fall in the ranking system. That's the ordinal scale. And there's a little more you can do with ordinal data than nominal data, but it's still limited mathematically. So let's move on to our third and fourth scales of measurement, our last two. And these two differ. It doesn't make a whole lot of difference with interval and ratio data, which we'll see next. As far as like the math that you do, most of the time, but there is a difference. So we want to point out that difference. So let's look at interval data first. So interval data, like it says here, there's an equal unit of measurement separating the scores. But the thing that sets the interval scale away from the next one we'll look at, which is ratio, is that with the interval scale, it says here, it doesn't have a true 0. So you can have a score of 0 on an interval scale, and it doesn't mean that the variable you're measuring is absent. Like a 0 is a possible score, right? So the best way to think about that, if you're measuring something like temperature, you can have it can be 0 degrees outside, right? And it doesn't mean like temperature is gone or absent. Like it's still there, and 0 was a possibility. And in fact, you can go below 0. So if you can have positive and negative numbers on a scale, that's an interval scale. Okay, so the 0 means that variable is still there. Now let's look at ratio. So a ratio scale, what it has in common with intervals, there's an equal unit of measurement, between the numbers. But in this case, a zero truly means that there is no amount of that variable present. So, like if I were measuring other physical things like height and weight, it's impossible to have a zero. You can't be negative in that case, and so there's a hard stop at one end of the spectrum at zero. So it's continuous up to a point, right? Up to a point when you're moving kind of on the left on the x-axis, you stop at zero. But like I said, it doesn't make a huge difference for a lot of the formulas we're going to do in our class. If it's interval or ratio, we can kind of put this together as one category, but you still should be aware of like what a zero means, right? I think I got an example of this. I'll give you a classroom example of like the interval and ratio scale. So let's say that I'm measuring your knowledge of the information from like the first 6 chapters in our class. That would be our exam number 1. So I wanted to see how much you know about, research methods and descriptive statistics. And I give everyone a test. And let's say I have these 2 different students that got a score of 0 on that test, right? So it was like 0 out of 50 points. Now, there can be 2 different types of zeros in my grade book. Now, remember, I'm measuring how much they know about the information from the first 6 chapters. So if somebody has a 0 in the book, it either means that they showed up and they took the test and they didn't get anything right, like absolutely nothing correct, right? That's never happened, by the way, but they got absolutely nothing correct. Well, I could say, well, that 0 means that variable still exists, right? Like that person showed up, took the test, earned a 0, and that's their actual grade. It's their actual assessment of their knowledge for that topic. So we might argue that's interval. We say that's interval data. Now, a ratio scale, what if there's a student who has a 0 in the grade book, but it's because they didn't take the test, and I have to put a 0 there because it's past the due date. Now, do I actually know anything about their knowledge on the first 6 chapters in the class? Are they based on their score from exam 1? No, I don't, right? So that 0 means there was an absence of that variable. I never actually got to measure them, right? So it's still a 0, but the 0 means something totally different as far as like the information that it gives me. So there's different ways to treat your zeros. And in the ratio scale, there was no test to actually grade, right? The variable is essentially absent. But an interval scale, that means a student showed up, took that exam, earned that 0. I know how much they know or don't know about the material. But like I said, the interval and ratio types of data in our class, we're essentially going to treat the same. But we want to be aware of like what a 0 means. And maybe that means like, when do I exclude this 0 from my calculations and when do I keep it in, right? So that's important to know from like a methodological point of view, right? For data management. So what I encourage you guys to do is to think of your own examples of nominal, ordinal, interval, and ratio data. Because if you think of your own examples, then that'll be a good a good way for you to process the information in and out of your own memories. My examples are fine, and if you use them, cool. If they were useful for you, but go on Google, try to find somebody, go in your textbook, start there in your textbook, and try to think of your own examples of these 4 scales of measurement. Okay, so not all data is the same. It means we don't display all data in the same way. But before we get into that and looking at like shapes of data, let's look at creating a frequency distribution table. So if we have a lot of data and we need to organize it somehow, there's some basic ways to do that. There's a lot of basic ways to do that actually, but we're going to look at starting with a simple frequency table, and then we're going to build onto that and get a slightly more complex information, from the same data on our table. But first, the new notation for today, there's not a whole lot. There's F, we want to know the frequency of times that a score occurs, and there's N, we want to know the total numbers of scores. And based on that information, we can create things like proportions and percentiles. So that's what we're going to do today with this table. It's going to have, what's it going to have, 4 columns on it. So we'll have 4 columns of information. And even though it's a table that we're making, it's still considered, overall classified as a distribution. So distribution, we usually think that means a graph, right? But tables and graphs are both distributions, just different types. Because the distribution is just, it says here, the general name for any organized set of data. So we organize it in a way so that it's not overwhelming for us. But I'm not going to give you a huge overwhelming data set to begin with, right? We're going to start with a smaller one. All right. So the first thing we're going to do is make a simple frequency distribution. And all that does, the name is perfect. It really is simple. But a simple frequency distribution shows the number of times each score occurs in a set of data. So it shows you, okay, these are the scores that exist in the data, and here's how many of each of these scores exist in our data set, right? So here's the score, and here's the F for that score. The F is just how many, right? How many of those? Okay, so it's a simple, sorry, the F is the symbol for a score's simple frequency. So let's take these raw scores here. And we want to organize these in a way that isn't so overwhelming. I mean, this one's not too bad. It's not a large amount of scores to keep track of, so it's not too complicated that way. But that's also not very realistic for most types of science that use statistics as their analytical tool. So you multiply this tiny data set by like tens, let's say multiply this by like 50, and that's how much data you usually have in the data set. And then it'd be really hard to figure out how many fours there are, how many twos and threes without some kind of management system. So that's what we're going to do next. We're going to do just a simple management of this raw data. Raw data, if you hear that, by the way, that just means this is like untouched data. We haven't organized it in any way yet. It's still in its raw form. So what we're going to do is create a simple frequency distribution, and it's just going to show us what scores exist in the data, and then how many times each score occurred, right? So let me switch my camera view, and that's what we will do now. Let's see if this works. Whoops, let's try a new share. Hold on, stand by with technical difficulties. There we go. That's a little better, huh? All right, so we're going to take that data from the number line that was on the previous slide, and we're just going to organize this in a way that's easier to make sense of the data. So I'm going to create 2 columns. I'm going to create an X column and an F column. So in X, we're just going to keep track of the data that does exist in our data set. And I usually like to go from the largest number first and then work my way down, but it doesn't matter. You can go either way, right? As long as you're consistent. So I can see there's a 5 there. I can see there are 4s in my data set. There are 3s, there are 2s, and there are 1s. So it's a small range of data that exists here. Okay. So the next thing we're going to do is we're going to count how much there are of each one. So how many 5s are there? Well, I got 1 5, right? There we go. And then how many 4s? Well, I got 1, 2, 3, 4. Right? 4 4s. How many 3s? 1, 2, 3, 4. 4 3s. How many 2s? 1, 2, 3 2s. And then how many 1s? 1, 2 1s. So did I miss any? It looks like I got them all. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Cool. So I got all my scores. And all we can really pull out from this information is what scores exist and how many of them are there. So you can say, well, 5 is the most rare. There are fewer 5s than any other score. And then 4s and 3s, equal parts. There were 4 of both of those, right? Not a whole lot you can do with this simple frequency distribution, but imagine how you had thousands of 1, 2, 3, 4, 5s. This would be much easier to look at than a raw score of thousands and thousands of these digits. So the only other thing we can pull out here is n. So we can say our n is 14, 14 total scores. And you get that by adding up the frequency column, right? Total scores are the frequency column added up. Cool. Okay. So now the next thing that we want to do here is work on this table a little more. So we've got some very, very simple information. Let's get a little bit more information now. All right, now the next thing we're going to calculate is something called the relative frequency. Right, so we want to find, or RELF for short, right? Sometimes RF for short. It's the, like it says here, the proportion of time that a score occurs. So the relative part, that means relative to the other data in the data set. How common is a score of 2, for example? So it means a score of 2 relative to this data set. Here's the frequency that we can expect. So to figure that out, the relative frequency, it's a real simple formula. It's our first formula for our class, right? We're just going to take the F for each score, so the frequency of each score, and then we're going to divide it by the total number of scores, right? So it gives us a nice proportion that way. Okay, so I'm going to switch back now to my table and we'll make a brand new column. So in your notes, you can make a brand new column. I'd say copy this formula down so you know how you got the numbers for the column, and then add these um, relative frequencies in a third column on your graph. I'm having the hardest time switching between my cameras for some reason. Let me see why. What's going on here? No. I'll do it this way. There, that works. Okay. Okay, so we're making a new relative frequency column. Let me pull my calculator out for you, as I'm sure you're about to pull your calculator out too. So for the relative frequency, let's do this. All right, so here's my calculator. Ooh, that's a little blurry, a little hard to read. So we're going to go one at a time. We're going to work our way up this column and just fill in the blanks. So we know our formula is F divided by N. So we're just going to do 2 divided by 14 equals, is that right? Let me try one more time. 2 divided by 14, yeah, equals 0.14. There we go. So the relative frequency of getting a score of 1 is 0.14, right? And we're just going to work our way up until we fill in the entire column. So we'll do 3 divided by 14 gives us 0.21. Right? And do the same thing for a 4. So 4 divided by 14 equals 0.29. Now it's going to be the same number for both of these because they have the same frequency of 4. And then the last one we're going to do is 1 divided by 14 equals 0.07. There we go. So relative frequency accomplished, right? So now we can say the relative frequency of getting a score of 5 is 0.07. That's a little weird because we didn't really talk in proportions like this. Relative frequency is a proportion. We like percentages more. So instead, you might say, well, 7% of the scores are 5s, or 29% of the scores are a 4, 29% of the scores are a 3, 21% scores are a 2, 14% of the scores are a 1. That's probably more like how we speak, in our everyday language. But there you go. Relative frequency is expressed as a decimal. So now let's go back to, now I'm getting the hang of it. All right, go back to our slideshow here. The next thing that we want to do, or we want to calculate, is the cumulative frequency. Easy for me to say. The cumulative frequency is how many scores exist at a spot on our table and below, right? So it's like how many scores are a score of 1 or less, right? How many scores are a score of 2 or lower? So it tells you like the raw amount of scores at a certain point on your in your data and below. So once you put them in rank order, like we already have on our table, that makes things a bit easier. So let me switch now to, there is a formula for this, by the way, for cumulative frequency, but I've always found it to be really confusing and tougher than it needs to be for students. So let me explain to you the easiest way, I think, to calculate cumulative frequency. So we're going to start at the bottom of our table. So we got a score of 1, and there are 2 of them, right? So if you ask yourself as we move our way up the table for cumulative frequency, how many of these scores are a 1 or lower? You would say 2, right? Because there are 2 ones. And there's nothing lower than a 1, so we can stop there, right? How many scores are a 1 or lower? 2 of them. So we matched, right? 2 and 2. Now if we say, well, how many scores are a 2 or lower? Right, then we go, well, there's 3 2s and there's 2 1s, so that's 5, right? 3 and 2 is 5. So a total of 5 scores that are a 2 or less than 2. 3 plus 2 equals 5. And then we're just going to work our way up. So how many scores are a 3 or less than 3? So we go, there's 4 3s, there's 3 2s, there's 2 1s. So we go 4, 5, 6, 7, 8, 9, right? Just add them up. So 9 scores are a 3 or lower. How many scores are a 4 or lower? Well, we go, there's 4 4s, there's 4 3s, there's 3 2s, there's 2 1s. So we go 4 plus 4 is 8, 9, 10, 11, 12, 13. Okay, so 13 of the scores are a 4 or lower. And then what about a 5? How many scores are a 5 or less than 5? Well, it's going to be all of them because 5 is our highest number. And there's 1 5. So we're going to add up all of the frequencies, and that should match our n, right? So the top of your cumulative frequency column should be the same as your total number of scores down here at the bottom. And that might be useful. Like, let's say that this was, a class. Say I'm teaching my class, and I want to know, well, how many actual students, not proportion of students, but actual students, got a passable grade on a quiz. And let's say like a passable grade on the quiz is a 3. I'm like, well, how many scores are above a 3? Well, it's only 5. So I'd be like, oh man, only 5 of these 14 students passed the exam. So there's some use for the cumulative frequency, but honestly, the cumulative frequency is usually thought of as just like a stepping stone in order to solve something that you're probably more used to hearing, which is the percentile. So usually what people want to know ultimately from these tables are proportions, right? So like the relative frequency and then percentiles. It's usually what people are looking for. So a percentile is similar to the cumulative frequency in some ways. Like you want to ask yourself how many scores are at this point and below it, but it's not giving you the raw scores that you would get from the cumulative frequency. It's giving you the percentile, right? So it's like what proportion of scores are at a certain point or below it, not how many actual raw scores. So it's a little bit different in that regard. But the formula is easy, so that's good news, right? You just take the cumulative frequency, which we just copied, and then divide by n, total number of scores, which we already know, and then multiply by 100 to put it back into the shape of a percentage, right? Okay, so let me switch back to my homemade document cam and show you how to do that. All right, so here's our formula down here at the bottom. And we're going to take the cumulative frequency numbers and plug them in one at a time here in the top of our in our numerator. Our denominator is 14, so we'll put 14 there in the bottom, then we'll multiply by 100. So we'll do these parentheses first, and whatever answer we get, we'll multiply by 100. Let me get my calculator out. Hope no juicy text messages come in while we're talking. Okay. So the first thing we're going to do is I'm going to take the cumulative frequency in the score on the bottom, which is a 2. So I'm going to do 2 divided by, whoops, I hit divide too many times. 2 divided by 14, which equals 0.14, right? Then I'm going to multiply that by 100, and that's going to give me a 14.29. I'm going to round that to 0.29. All right, so we got that. Now let's keep moving up. We're going to keep moving up this table until we're done. And here I'm going to put percentile. That's really sloppy. Okay, so we're going to do next 5 divided by 14 equals multiplied by 100, 35.71. Okay, now we're going to keep going. So next we have 9. We do 9 divided by 14. Gives us 0.64 times 100, 64.29. There we go. And we're almost there. Now we're going to do 13 divided by 14. So we get a point, what is that, 0.93. We're going to multiply that by 100 to get almost every score, 92.86% of the scores, right? And then on top, of course, then we have 100, right? Because all the scores are 100 or lower. So the way you would read this is, what percentage of scores are a 1 or less than 1? Well, it's 14.29% of the scores, right? How many scores are a 2 or less than 2? Well, it's about 35.71% of the scores. How many scores are a 3 or lower? 64.29. How many scores are a 4 or lower? 92.86, right? How many scores are a 5 or lower? Well, all of them, because 5 is the highest number. Right, so there you go. There's a frequency distribution table for you. Not too complicated. And a much better way to look at, lots of data than just to look at them in their raw form, which essentially be impossible if you have, a lot of data. All right. Now, for the rest of this chapter, we don't have any more math to do. And I know that makes some people very, very happy. That's as tough as the math gets so far in these first 2 chapters. But we're not quite done with the PowerPoint. So let me go on. We want to talk about shapes of data now. So now that we know how to make one type of distribution, which is a table, that's great. And let's also talk about graphs, right? So the next thing we want to go over is creating graphs. And the goal of a graph is to communicate, big ideas within your data, to describe your data in simple form so that it's easy for your audience to understand, right? So when you look at a graph, you should be able to look at it and go, I get it, right? I get it. That makes sense to me. That graph is really easy to read. So we're going to put, there's some basic rules for you. On the x-axis is where you put, the scores that exist in your data. So it's like what scores do exist. So if we're looking at our last table, this will be our x column, right? Our x column goes along the bottom. And then on the y-axis going up on the graph is the frequency. So we would do x and f if we were to graph our data. And there's different ways we could do that for a simple frequency distribution. There's a bar graph, a histogram, a polygon. And so we can talk about these 3 basic forms of graphs and when you're supposed to use each one. I didn't learn this stuff until I think I was actually in grad school. I mean, I'm sure I had a professor that taught me when I took stats, because I took a few stats classes, but I don't remember that being ever explicitly told, like, okay, a bar graph communicates this type of information and here's when you should use it. I learned it in grad school. My professor said, why'd you use this graph? Right? I said, I don't know. It looks good. It makes sense, doesn't it? He's like, yeah, but this should really be a histogram, not a bar graph. I was like, okay. Right. And he told me why. And I felt really dumb. Like, oh man, I wish I'd learned that earlier. So I'm going to tell you guys. And it's not that tough. It's not that tough to understand at all. All right. So the first type of graph, let's do this, and we'll do this in the as close as we can to the order of the scales of measurement I showed you guys earlier, like nominal, ordinal, interval ratio. So we talked about nominal data first last time. So now let's look at graphs that are usually associated with nominal data. And those are bar graphs, right? So bar graphs are called that for a simple reason. You have bars on your graph. but they do communicate something particular when the bars don't touch each other, like in this graph here, right? So that means that your variables are discrete, right? I show so the your x-axis, those are it's a discrete variable you're measuring, meaning that you can be in one group and only one group, right? So nominal data. And political affiliation is a good example of that. So if you're registered in a political party, they don't let you pick two. You can't register for more than one at one time in any state in our country. So you got to pick one, right? You can't kind of like straddle the line, even if in your real life you're like, well, I like some things about the Republicans, I like some things about the Democrats, and then I don't like some things about both parties, right? Then in real life you might be kind of like straddling a line there. But when it comes to the math, or even like survey research, the reality is you can only be registered as one of them. So that works, right? It's nominal data. Okay. Um, but yeah, this is one of those things I didn't know until grad school. It's like, oh, that's why bars don't touch. That makes sense. There should be daylight between them. And it's supposed to tell your audience, hey, you can only be in one of these categories at a time. Okay, now moving on, looks almost like a bar graph, except for you can tell now, of course, the difference is the bars are touching each other with a histogram. So with a histogram, usually we'll see this with interval and ratio data. And the bars touching each other is supposed to indicate that you can actually like be right on the cusp of two categories, or essentially like in two categories at once in that case. So like if you looked at this graph here, and let's say it goes in like 10-point intervals, like 0 to 10, and then 10 to 20, and then 20 to 30, 30 to 40, and so on. And they're color coded. So let's say that you have a score of 60, and that means you're like right here on the cusp, right? What group are you in? If you have a score of 60, are you in this kind of like orangish group, or are you in this bluish group? Well, you're kind of in both, or you could easily probably sway either way in a different context. And that's okay, right? That happens. That's real life, right? That's interval ratio data, a little more powerful in the type of data, the scale they're measured on. So it's continuous. So it means that you can kind of be right there on the cusp. So the other thing though, when you use this graph, the histogram, where you have bars and they touch each other, you usually use that when you have like a minimal amount of categories or scores on your x-axis. So like this is a good example because see how many categories we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10's not difficult to keep track of. Like I can look at this and I can see that all the colors are different, and it's still kind of aesthetically okay, right? It's pleasing to the eye enough. It's not confusing. So it's still considered a pretty good communication tool. So, okay, we have 10 categories here, but now let's say that maybe this exam went up to like 400 points, and then you've got 40 bars that you're trying to put on one graph, and all these bars touch each other. There's 40 different colors. It's like now it's starting to get confusing. It's hard to read. Something might be better than bars in that case. And if you have that many categories on your x-axis, then you're going to go ahead and use a polygon, or sometimes called a line graph instead, right? So it's interval data, just like with the histogram, that they have in common. But in this case, like imagine this, if we're going from like 57 to 76, if these were all little bars at each of these hash marks here, that would be really, really cluttered and hard to read. And we don't want that, right? The goal of the graph is to communicate quickly. And if there's a lot of categories on your x-axis, then you want to go ahead and use a line graph instead, called a polygon. When in doubt, though, by the way, like if you're ever thinking like, what's the number? Like what number says like this is too many, now I should use the polygon? There is no set number for that, right? So it is kind of subjective. So like when in doubt, use a polygon if you're trying to decide between using a polygon or a histogram, because you will never go wrong, right, with the line graph or the polygon. But if you're like, well, to me 20 categories isn't that bad, somebody else looking at it like, oh, I'm totally confused and overwhelmed by this graph, you shouldn't have 20 bars on it, right? Well, maybe get some opinions from other people. Right? It's kind of a weird one. It's a little subjective, right? It's about aesthetics and communication in that case. But when in doubt, then use a polygon. Okay, a couple other things in this chapter about shapes of graphs. So we're going to be dealing a lot with something called the normal distribution or the bell curve or the normal curve. And you guys have seen these before. I am sure we talk a lot about recently with the pandemic, like flattening the curve. This is what they're talking about. So that big hump in the middle, trying to bring that down. Um, but there's some basic things about the normal distribution for today that I want you to know. And we're going to see it a whole lot. So the first thing I want you to know, let's talk about just like the shape itself and what it tells you. So a bell-shaped curve or a normal curve or normal distribution like this one, it's symmetrical. So that means if you were to, slice it right down the middle, you've got a mirror image of itself on the right and left, right? And then the other thing, of course, is that the peak here in the curve, means this is where most of the data lies. So most of the data in this case for these test scores is right in the center. And as you move in either direction away from the center to the right or to the left, as scores get lower to the left and higher to the right, the scores are more extreme as they move away from the center, meaning there are fewer people that have them. So as we move to the left, those scores exist and they get pretty darn low, but as they get lower and lower, the frequency gets lower and there are less and less of those scores. As you move toward the center, you have an increase of scores. So that the majority of people right here in the middle. And then you have, as further you go to the right, scores get higher and higher, the frequency goes down, there are fewer of them, and you've got some extreme outlying scores, in both directions. So you've got the body of your graph right here, of this distribution here, right here in the middle. And then you got the tails out here where these extreme scores lie, these outliers are. They exist and they need to be accounted for with interval and ratio data. However, there aren't very many of them. Okay. The other thing about normal distribution, not just some characteristics of it. I want to talk about like why we use that so much in an intro to stats class. And there's a couple reasons. The first reason is that if for a lot of things in nature that you measure, not everything, but for a lot of things, and human behavior included, you get bell curves from people. If you measure enough people, right, you'll get a bell curve from them. Meaning that the majority of scores typically fall somewhere in the middle of these scales with extremes on both ends. So that's a good reason, right? I mean, for a lot of things we measure, we get these bell curves, which seem to look like they occur naturally in the world. So that's a good thing, right? It means we can, feel accurate in using this curve for most things we measure, but not all things, right? And the second reason that we're going over the bell curve right now is because it's the easiest, honestly. It's the easiest to apply statistical properties to when you're learning about statistics. And so you guys are going to see the bell curve a lot since this is an introduction to statistics course. So two reasons, right? Curves in nature, and it's easiest to learn about statistical processes with the bell curve. Okay, but not all curves or not all variables that you measure will give you a bell curve. Sometimes you do end up with skewed distributions or distributions of shapes that are not bell curves, right? Skew distributions are important to think about because if you think of who's represented by a distribution and you get something that's skewed and this has something to do with people, then it means that most people on a negatively skewed distribution, for example, in this one here, most people are scoring like high, moderate to high on whatever it is you're measuring. Now, there are these extreme low scores out here, but there's not very many of them, right? So you can think about examples of negatively skewed distributions. And I would want you guys to think about this too, right? We could say, here's one. Age at retirement. Let's say on the x-axis down here, it says low, middle, high. Let's say these are ages, right? So it means the older you get, and over here is the frequency of retirement. So the older you get, right, the more likely it is that you're going to retire if we look at descriptive data, because that's when most people do retire, right? When they're a bit older. Some people retire young, right? According to if this were our example, but not very many, right? They're on the low end. They exist, but a very low frequency. Maybe they're people for some kind of medical reason needed to retire and can no longer work, or maybe they won the lottery, something like that, and they decide not to, or they inherited a bunch of wealth, right? Who knows? But there's not very many people in that category. Most people, it's not until you're past middle age that you retire. For some people, way past middle age, right? Okay, so this would be considered, this is called a negatively skewed distribution, because what's skewing the data are these low scores, right? So it's going left or toward the low scores and the negative. That's where the outliers are. Most of the scores are over here on the right, but the name negative skew comes from the outlying data. So it's these low scores that are skewing, this distribution negatively. And then we can flip it around for a positively skewed distribution. In this case, most people score low to moderate, and there are some people that score high, but there aren't very many of them. They do exist, but they exist in a low frequency. And their scores, these outlying scores, are skewing the data to the right or to a high direction, and we call that a positive skew. So the idea I think is easy. It's like this is where the scores pile up, where you see the big peak, and then you follow the tail down, and that's where the name of the distribution comes from. The concept's pretty easy, but it's easy to, what happens in the past when I look at student scores is that they get the names mixed up between positive and negatively skewed, right? So just remember, the name comes from, where the outliers are. Okay, now we'll look at these distributions later in class too, because when we get into something called central tendency, the shape of your data really matters for how you determine where the center of your data is. So we'll talk more about that in a couple of chapters. So we'll come back to this idea about normal curves versus skewed curves. All right, just a couple other shapes to look at, and I'm not going to go over these in the analyses with you in the class explicitly, but they might show up, and so it's good to talk about them, at least mention them. So you might have a bimodal distribution. That means mode is where the highest frequency is within a distribution, or the peak, right? The peak in the graph. So a bimodal distribution just means you have two peaks. So you got these two scores that occur the most, and they occur at the same level. So it's hard to say where the peak is. There's two peaks essentially. That's okay. I mean, that happens in data. The weird thing is that this is still symmetrical. This is one on my PowerPoint here. If you were to cut this in half, you do get a mirror image, but it's not considered a normal curve just because it's symmetrical. It's got to have, that normal curve shape. So two distinct humps. That might happen, right? I mean, that could happen for lots of reasons. Let's say you were going to buy a new car. That sounds good, right? I want to get a new car one day. Let's say you're going to buy a new car and you're thinking to yourself, well, what's important to me in a new car? And then you survey a bunch of people and you ask them what's important in a new car, and they tell you, well, what I'm looking for. Maybe get two things that show up as the most important. Maybe it's something like gas mileage and safety. I don't know, something like that, right? So you get gas mileage and safety, both important and equally important to you. It's other things that are on this graph. You get this little valley here as you're moving up this slope toward the highest peaks on both sides. Like, you get other things that are important, but maybe not as important. You get these two in the middle, and that's okay. All right, so I'm not, like I said, I'm not going to examples using bimodal distributions, but they do exist. They do show up, so it's good that you have the language to talk about them. Okay, now, whoops. The last thing we'll look at is something called a rectangular distribution, and these are really difficult to interpret, right? So rectangular distribution, you can tell why it's called that. It means that you have the exact same frequency of every score. So there's no peak or valley. If you took an average, these scores would tell you something, average score is right in the middle, but that'd be misleading because if this were grades in the class, it'd be like there's just as many Fs as there are Ds, as there are Cs, as there are Bs, as there are As. So if you were asking me like, how'd the class do on the first exam? And this is what the exam scores look like, I don't know how to answer that question. Like, how'd the class do? I'd be like, man, they did all right. They did every score you can to the same frequency. So it's hard to interpret that. And although this is not a ceiling or floor effect, has the same difficulty with interpretation. So a ceiling effect or a floor effect means like everybody scores high if it's a ceiling effect, or everybody scores low if it's a floor effect. So if I was like, fill out this survey and how racist are you, we're going to get a floor effect, right? Because everybody's going to go, not me. On a scale of 1 to 5, how racist are you? We're going to get a bunch of ones, right? So we're going to get this floor effect. And then on the ceiling effect, would be the opposite. If it was like, that's tougher to think of. Everybody to agree on something, right? I would say like, yeah, that's bad, right? Everybody has the same idea. That would be a ceiling effect. Um, I mean, those happen in data. Yeah, that usually means either you're asking somebody a really obvious question, or we talked about validity in the last chapter. Um, and reliability probably means like your materials are maybe not suited to try to answer that question if everybody's scoring one way. That just doesn't make sense. Human behavior is not that simple, right? Okay, so we went over quite a bit in this chapter about different types of distributions. I hope it's not too daunting. I will ask you on the first exam to create a frequency distribution table, or at least answer questions based on one. And so we'll review that idea a little bit. I'm going to make another video for you next week that's going to involve the software component of our class, where you're going to create this type of table in either Excel or SPSS. So we will review this idea a little bit again at the end of next week. And thanks for tuning in. I will see you guys in the next video. Bye.